In the previous module, we had discussed how the general linear model can be fitted either as a regression model or as an analysis of variance or ANOVA model, or as an analysis of covariance or ANCOVA model. Now, while fitting a general linear model to a regression setup, we have a number of assumptions which need to be satisfied before we can decide on fitting the regression model to the data. In this module, we will discuss 5 such assumptions, and also we will check whether each of these assumptions are satisfied for one example data set, and we will also discuss the different ways and means of generally checking these assumptions while fitting a regression model. When we fit any kind of statistical model, there are basically 2 different approaches that we keep in mind. In the first approach, we define the population of interest. We define the population from which we want to get our y and x variables. We then state the scientific questions and underlying theories. So we define the brief objective of the study, and also we define the variables which we want to collect from the defined population. We then describe and explore the observed data. Some basic exploration of the data is done before we start fitting any form of statistical model to the data. And we then define a model which we think would best fit the data at hand. This model happens to have 2 parts. The first is the probability part, which is taken care of by the error in the GLM format, which is y equals x beta plus error. And the second is the systematic part, which is part of the x variables which are fixed. The x variables are the independent variables. We have fixed collected data from the population for these variables, and using them we try to define the model for the response variable y. In the second approach, where we come to the statistical inference part, after fitting of the model, while fitting the model, we estimate the parameters in the model, where we fit the model using the observed data. Once we have the fitted values of the parameters involved in the model, we then make inferences about each of the covariates. We check the validity of the model. We verify whether all the model assumptions are met with. We then accordingly redefine, refit, or recheck the model if it is necessary. We then interpret the results of the analysis once we get the final robust statistical model. In this module, we will discuss the different model assumptions which need to be checked in order to validate the model which we have fitted to the given data set. Now, for model validity checks, we check that the assumptions of the linear model hold. Plots of residuals against the predictor is also made. We also check for the normality of the errors, and some of the global checks are adjusted R-square, AIC, and BIC. We will later on describe what each of these criteria are and how they come in handy when checking the assumptions for a linear model. So let us first look at the assumptions which we make before fitting a regression model. So the model, as I said, can be written in terms of y and x in the following form. yi equals beta 0 plus beta 1 xi plus epsilon I, where xi represents the independent variable or the systematic part, and epsilon I represents the error. The first assumption is that there is a linear relationship that exists between the x and the y. And also we assume that the observations that have been taken from the population, they are independent of each other. This is also one of the assumptions for fitting a linear regression model. The third assumption is that the error terms, which is the probability part of the model or the random part of the model, that is normally distributed, and the normal distribution has a mean 0 and variance sigma square. And the fourth assumption is in terms of these variances. We assume that for the error term which follows a normal distribution, the variances are all the same across the different observations. In other words, sigma square happens to be the variance for all the epsilon i's or the errors. Now we will take each of these assumptions and take up one by one the different techniques of making sure that these assumptions are met with before we fit a regression model to the data set. So after we have listed these different assumptions, we will now talk about the different means of checking for these assumptions. So the first very basic way of checking whether these assumptions are met with is by simply plotting the data, and this plot can be one of the most powerful model checking techniques. From a simple plot of y on x that includes the fitted regression line or the trend line as we call it, we can check for linearity, normality, equality of variance, outliers, as well as the other assumptions. Now talking of the linear relationship, as I had mentioned before, when we take up the first approach of fitting any statistical model, we first create the scatter plot between the dependent and independent variables. So if I have one x and one y variable, I plot them against each other. In case there is a linear relationship, the pattern will be reflected by the scatter plot. In case I see no such pattern and it's only a scatter spread out of plots, then we know that probably the assumption of linearity between x and y are not satisfied. So if we want to check whether the linear assumption is correct, we look at whether the line that fits through these plotted scatter plots are close to these fitted dots or not, or we also check for outliers, whether there is any one plot in my scatter plot or any one data point which is further away from the rest of the cluster. So in order to access these graphs, if I have one x and one y, then we look at the plot of x against y or y against x, and we also look at the fit of the regression plotted against either the fitted values of y or the x variables. In case we have two or more than two x variables in the regression model, in other words, if we have a multivariate regression setup, then we look at the adjusted variable plots. What happens in adjusted variable plot is that we regress y on the x's, leaving out xi. We then regress xi on the remaining x's, and we get the residuals from both these plots. So once we get the residuals, we plot the first set of residuals against the second set of residuals. If they still show us a linear regression pattern, then we know that the linearity assumption between x and y has been met with. Now coming to the second assumption as to the independence of the observations from the population. So are all the people surveyed independent from one another? This cannot be assessed statistically or graphically, but we know that where the data has come from, if there has been a simple random process of collecting data or selecting respondents to collect data, then we know that the independence of observations assumption is also satisfied. Now the third and a very crucial assumption in linear model is that the error terms are normally distributed. So at every value of x, the observed point should follow a roughly normal distribution centered at the fitted value of y. At the onset of the discussion of regression model, or rather linear regression model, we have seen that the major assumption made is that for each given value of x, y follows a normal distribution with a certain mean value and a given standard deviation. So based on the fact that y follows a normal distribution, x beta being the systematic part, we are left with the random part, the error, which in turn becomes normally distributed. So for every value of x, the error terms also follow a normal distribution. So we assess this using the residual plots. We plot the histogram of the residuals after fitting a regression model, and if it gives us a roughly or approximately symmetric shape, then we know that the distribution is close to normal or a normal distribution. In addition to these, we can also look at the normal probability plot of the residuals. In this case, we expect to see a straight line trend in these probability plots. If this is absent, then we know that the assumption of normality of errors has been violated. So in case of the normal probability plot, the technique is to plot the similar normal distribution probabilities along the y-axis or the x-axis, and along the other axis we take the probabilities for the residuals that we have obtained from fitting the regression model. If these probabilities happen to be as close to each other as possible, or as we expect them to be, then we expect a straight line through the origin. In case we see such a pattern, we know that the assumption has been met with. Coming to the equal variance condition of multiple linear regression, at every value of x, the observed points should follow a roughly normal distribution with the same variance across all x's. This is also assessed using the residual plots. So once we fit a regression model, we look at the residuals and we plot them against the predictor x variable. Normally, if the assumption of equal variance is satisfied, then we expect to see a random spread of the residuals. But in case we have any pattern as to the increasing or decreasing pattern, or a funnel shaped pattern in the scatter of these residuals when plotted against x, we then expect a violation of the condition of equal variance. So on the slide we can see there are 4 types of assumption violation. In the first case, we have y plotted against x, but instead of seeing a linear pattern, we see what is called a quadratic or a polynomial pattern. In the second case, we have a linear pattern if we ignore the outlier, but because there is an outlier in the data set, the trend line which is fitted through the data has been influenced by it, and now we see that a line that has been fitted is wrongly fitted to the data set at hand. The third is when there is a violation of the normality of error assumption, where we see that when x and y are plotted, we see a particular pattern in the spread or the scatter of the plots. Almost all of them fall on the line. However, there are a lot of them which are mostly above the line. So there is no random spread, but there is a particular pattern. Also, in the last case, we see that when we plot y against x, the plot has a funnel shape, where in the beginning of x values, in the beginning of the range of x, we have most of the data clustered close to each other, and then symmetrically they start spreading out on both directions, causing a funnel shape in the scatter plot. So these 4 plots show us potential violations of the assumptions that are made when fitting a linear model. If any one of these assumptions are not satisfied, then fitting a linear model to the data will be a faulty model which cannot be used as a predictive tool at any given point in time. Now, when we come to the checking of the models through residual analysis, let us talk about the concept of standardized residuals. Now, talking of residuals, which are represented by the error term, which is nothing but the difference between the yi's, which is the observed values of my dependent variable, and the yi hat, which is estimated values of the dependent variable after we fit it into the model. So the model assumes that these error terms epsilon I, they follow a normal distribution with a mean of 0 and variance sigma square. So we know that the standardized residuals would be of the form epsilon I minus 0 divided by sigma hat, or the standard deviation, which is the most common way of standardizing any quantity by subtracting the mean and dividing by the standard error, where sigma hat square, which is the variance of the normal distribution, is also otherwise known as the mean square error. So the standardized residuals are supposed to follow a standard normal distribution with a mean 0 and variance 1. Now, if the model fits the data well, then we expect a histogram of the standardized residuals which should look like normal. We check for any asymmetry or any outliers. In case any asymmetry exists or there are any outliers which can be detected, then the assumption of normality of these errors has been violated. So a plot of the residuals versus the x variable should look like a random scatter or without any systematic relationship. A plot of the residuals versus the yi hat, which is the fitted values, should also look the same. In case it looks otherwise, then we know that the assumption has been violated and we have to look for ways and means to negate that. So on the next slide, we see the relationship between health status and pollution in 20 geographic areas. So we have in the first plot plotted the y variable against the x, where the y variable is the health status measure and the x variable is the pollution level. So if we look at the scatter plot, we see that there is a clear linear trend without any apparent pattern. So a potential linear relationship exists between the x and y, and it can be fitted using the linear model. Next, we look at the histogram of the standardized residuals with an overlaid normal curve. So if we look at the histogram, we can see that it has roughly a normal approximate distribution, where we have less frequency in the first half of the data set, which increases up to a point and then symmetrically decreases for the remaining values of the standardized residuals. Coming to the fourth plot, we plot the standardized residuals against the pollution level, which is x. So residuals plotted against the pollution level, we can see that there is a random scatter, as we expect if the assumption of normality of errors is satisfied. And the same is seen in the fourth plot, which is the plot of standardized residuals against the predicted health measure or the fitted values. So all four of these plots tell us that the linear model is potentially the best fitted model from the first plot, and once we fit the model, we can check the assumptions that have been satisfied by looking at the remaining three. So the conclusions that we can draw from the above plots are that regression scatter plot looks good, it looks linear, standard residuals appear fairly normally distributed, standard residuals versus x appear randomly scattered as is expected when the normality assumptions are satisfied, and the standard residuals versus predicted values also appear randomly scattered. That is, there is no apparent pattern and no extreme outliers which can be detected. Now coming to the next slide, where we have another four sets of plots, we are here trying to look at the non-linear assumption of a linear model. So in the first plot, we have y plotted against x in this example, and we can clearly see that the trend line which goes through the data points which have been plotted is not remotely linear. Now moving on to the histogram of standardized residuals with a normal curve overlaid on it. Now because in the first plot we have seen that there is no linear relationship between x and y, if we forcibly fit a linear model to the data, then we end up with a histogram for the errors which looks exactly like the second plot, which is a very skewed distribution. It is skewed to the left, and it is a departure from the symmetric distribution of the normal curve. So the normality assumption has been violated, which is also evident from the last two plots, which is the plot of the standardized residuals against the x variable and the predicted y or the fitted values. In both the cases, instead of seeing a random scatter without any pattern, we do see a particular quadratic pattern in the plot. So what conclusions can we draw? The regression scatter plot shows nonlinear relationship, and when we still fit a linear model, the standard residuals don't look normally distributed from the histogram. The standard residuals versus x as well as the predicted value also show a nonlinear relationship. Now in case there is an outlier in the data, that can also be checked through these plots which we have talked about already. In case there is an outlier, we have seen, if you look at the next slide, the first plot, we have seen this previously on one of the slides. It shows a data set where there is an outlier which is farther away from the rest of the observations. So initially for all the other data points, we should be able to fit a linear relationship between x and y. So a linear model would be pertinent, but that one outlier, which is a very high value for y corresponding to x equals 30, that tends to draw the line towards itself, influencing it to show us that there is an outlier in the data and that the linear model fitted to the model is not a good one. The same is reflected in the histogram of standardized residuals. Due to the existence of the outlier, when we fit a linear model, the resulting error terms or the residuals have a histogram which is skewed to the left. So because this is a departure from the normal distribution, we know that any outlier existence should stop us from fitting a linear model to the data. Also, if you look at the third and the fourth plot, which is the standardized residuals plotted against the x variable and the y variable, fitted y variables, we can see that there is a pattern which we do not expect to see in case the assumptions are all satisfied. So, the conclusion should be that the regression scatter plot which shows an outlier should not be fitted with a linear model. Otherwise, the standard residuals look normal, but there are large residuals present on one side of the values. Also, the standardized residuals for x shows a pattern and it shows the outlier, and so does the plot of standardized residuals versus the fitted values of y. Now, looking at non-normal example plots. Now, if y and x happen to have a scatter plot which looks like a non-normal spread, and forcibly fitting a linear model to this data will give us a histogram which looks like the second plot on the next slide. So the histogram of standardized residuals overlaid with the normal curve shows us a strictly right skewed distribution with very high frequencies towards the first few values of the standardized residuals and very little frequency for all the others. So when you overlay with the normal distribution curve, we can see that it is a departure from what we expect to see in case of a normal errors. Also, the third and the fourth plot shows us the standardized residuals plotted against the x and the fitted values, which also tend to show us a pattern which we do not expect to see in case the assumptions are all satisfied. So on the next couple of slides, we will see that the fourth assumption, which is the assumption of equality of variance of the error terms, when this is not satisfied, when this is violated, what kind of residual plots do we expect to see? So once we look at these patterns, they will tell us for future use what kind of pattern should we be looking out for in order to figure out which assumption has been violated while fitting a general linear model. So in the first plot, we can see that plot of y against x shows us the values which are very close to one another at the beginning of the scatter plot, but then they tend to spread out. So this is a violation of the linear pattern which we expect to see between x and y. We still fit a linear regression model. The histogram of the standardized residuals, however, do show us a somewhat normal curve which is symmetric in nature. However, if we look at the standardized residuals plotted against x and residuals plotted against the fitted values of y, we see what is called a funnel shape, which means all the points are mostly scattered towards the end of the range of data set of x and fitted values. However, at the beginning, they are all clustered close to one another. So the final conclusions would be regression scatter plots show increasing variability in the plot of y against x. The standardized residuals do look normally distributed. However, standard residuals versus the x and the predicted value show increasing variability because initially they are all close to one another, and slowly as we increase the value of x and fitted values, the values started to get, the scatter plot starts getting wider and wider. So now taking an example of wage data, if we want to fit a linear model to the data set where the response variable or the dependent variable is the salary or hourly wage, and the x variable which will explain our dependent variable is experience. So the estimated equation or the prediction equation for y is given by yi hat equals 8.38 plus 0.04 times experience for the ith observation. So if we look at the residuals versus the continuous x, we will use to access the remaining relationship with the data. We check for the assumption of linearity. So we can see that when the data set that we talked about of hourly wage and experience, when it is plotted, the line has been flattened out. Most of the data points are lying almost parallel to the x-axis. The residuals are centered at 0. The horizontal line shows how flattened the regression line is. So we look at the residuals after fitting the regression model. We fit it against the years of experience, which is the x. So from here we can see the actual residuals. It's hard to tell which points are extreme. It is hard to find which ones are outliers. So we look at the standardized residuals. We look at the ones which are greater than 2, and we look at the standardized residuals which are greater than 3. So it so happens that 5% out of all the observations have standardized residuals greater than 2 and 1% have standardized residuals greater than 3. So we can safely say that not a lot of outliers exist in the data set, because most of them fall within the 2 standard deviation or 3 standard deviation limits. So when plotting our residuals against x, it's fine when there's only one continuous x in the model. But however, in case of a multiple regression setup, if we have multiple x's, instead of fitting the residuals to each of these x's, we rather plot it with the fitted y values, because the fitted y value is calculated based on a linear model, which is a linear combination of all the x's. So it's one and the same thing to look at the residuals plotted against each x or the residuals plotted against the fitted values. The idea is to look at the pattern. If there is any pattern, then we know that the assumption has been violated. If there is a random scatter, then the violation of assumption has not happened. So if there is a linear relationship or not between wage and experience, that can be seen by checking whether the wage experience model appears to fit well. There seems to be a residual pattern for people with very less experience. So towards the initial values of experience, we can see that there is a particular pattern which could be taken care of by adding a spline to allow for non-linearity. And there is also one potential outlier. So we should go back to the data and check the entry and information for that particular person. Now we see one outlier towards the lesser experience values. So the outliers are far from the pattern of the rest of the x's, may affect the line. And the regression line always tries to go through the mean of the x variables and the mean of the y variable. So an outlier near the x will not influence the line very much, but if we have an outlier which is far away from the mean of x, as in this case we can see, it will draw the line towards itself. So this cannot be used as part of the observation which we use to fit a data set. If we take care of that one outlier, then the remaining data set will help us fit a regression model which can be better used as a predictive tool. So are the observations independent for the wage experience data? This cannot be assessed graphically, as we have mentioned before. So the data were collected by random sampling of the workers, so we can assume that they were independent of one another. Non-normal residuals, whether the residuals which came from fitting this regression model, they were satisfying the normality assumption or not, the parameters estimated are still correct, but the confidence intervals that we get for these estimates would be misleading in case there is non-normality of the errors. So we can think of including additional predictors sometimes to solve this problem of non-normality of errors. Another solution is to transform y. Sometimes when any one of the linearity assumptions are not satisfied, then we try to transform the y variable or transform the x variable so that we can then fit the linear regression model to the transformed variable, and that will show us that all the assumptions of linearity have been satisfied. So log of y or square root of y draws in data skewed to high values, or we sometimes take 1 divided by y or 1 divided by square root of y draws in data skewed to low values. We can use transformed y instead of original y while fitting the data, but the interpretation for parameters should also be done according to the transformed y. For instance, if we take log of y as well as log of x in a linear model, then the interpretation of the slope coefficient then becomes the elasticity coefficient for y, which is nothing but the relative change in y divided by the relative change in x instead of the absolute change, which is the slope for a linear regression. Now what happens if the variance is unequal for the data set? The parameter estimates are valid, but the confidence intervals would be misleading. Also, additional parameters may solve the problem, which translates to the fact that we can include more x variables in the model, which will reduce the violation of the assumptions. So assumptions in simple linear regression model, we have one predictor, that is one covariate x. In case of multiple linear regression, we have more than one covariate. So y follows a normal distribution with a certain mean mu and a certain standard deviation sigma square, where the mean mu will be given by the expected value of y given the different values of x, which is beta 0 plus beta 1 x1 plus beta 2 x2 plus beta p xp. In the example, since we have wage and experience, and from the fitted data we have seen that some of the assumptions of linearity are violated, then in order to take care of the linearity assumption violation, in addition to experience, we can also add some more factors like age, gender and education. So we translate our simple regression model to a multiple setup, and now after fitting the model we can further check whether the assumptions are satisfied or not. In this particular module, we have discussed 5 different assumptions which we make before fitting a regression linear model to a data set. All of these assumptions have been explicitly discussed as well as demonstrated using numerical examples. All the numerical examples and the data fitting have been done using the statistical software R, and the output from these model fitting have been explained. Also, the plots have been explained in order to demonstrate how these assumptions of a linear model are checked while fitting a regression model to a data set.